The classical choice of branch cut for the complex square root is just asking that the real part of the solution is bigger than 0. Now what we're going to show in this exercise is that this is equivalent to imposing that the angle of z is in the interval between minus pi and plus pi before we halve it to calculate the square root. So just pause the video and think about this for a while. Okay, so if we want to calculate the square root, we have that f of z is z to the power of 1/2, and the result is our w. So we go from the z-plane to the w, and then we restrict our solutions to real parts of w being positive. Now, if we want to express this in terms of angles, what we can write is we can write z as rho exponential j theta. And then we can just calculate w by taking the real valued square root of the argument rho, and then just taking the angle theta and dividing it by 2. Now you also know that if in the z-plane you just add an extra factor, an extra 2 pi to our angle theta, that this will not make any difference. So this point z just stays where it is, even if you add multiples of 2 pi. However, if you now use this expression to naively, straightforwardly calculate the square root, you will end up with the square root of rho exponential j theta over 2 times exponential j pi. And this exponential j pi is, of course, -1. So here you clearly see that the reason this second solution appears with a minus sign is because we have the freedom to also add 2 pi to the argument in the z-plane. And then if you just calculate half of the angle, we end up with a pi phase shift with a factor of -1. Now, what we would like to show now is that if we restrict our theta values in the interval from minus pi to plus pi, then we will end up exactly with the solutions where the real part of w is positive. So in order to show that, what I suggest we do is we look at 4 specially placed points in the z-plane. So if we have here a point z with a certain radius and a certain angle theta, then let's have a look at 4 different points. So one of them is just above the real axis over here, just above the negative real axis, just below the negative real axis, and just below the positive real axis. So for these 4 points, what I would like you to do is fill out a table like this, for example, where for the 4 points, 1, 2, 3, and 4, we calculate their angle theta, which is an angle in the z-plane, of course. Bearing in mind that we restrict theta to the values minus pi and plus pi. And then to calculate the square root, we will calculate theta divided by 2. So this is something that will give us a location in the w-plane. And then based on that, try and verify that indeed you have the real part of w being positive, and that you also have the traditional choice of branch cut, namely the negative real axis. So just pause the video and work on this for a while. Okay, let's have a look at the point 1. So if we have our argument over here, we just go to slightly above the real axis, and then you see that this is just an angle equal to 0. Same is true for 4. That's just an angle slightly below 0, but in the limits of really ending up on the axis, both 1 and 4 will give us a value of theta equal to 0, which is in the interval minus pi plus pi. So that's fine. For these 2 guys, you write 0. So let's now move our angle to the point 2. So we keep on increasing the angle until we're just above the negative real axis over there. And we see in this case, we're just short of pi. And in the limit for the point 2, we will end up at pi, which is indeed in the interval minus pi to plus pi. Now, if we're in the point 3, one thing we could say is that we keep on increasing our angle so that pi just becomes pi plus epsilon. So we're slightly above pi, but that's not our recipe here because we want to restrict our angles in the interval from minus pi to plus pi. So rather than using for the point 3 pi, we're going to use minus pi. So this basically means that our angle here will start at minus pi for 3, and then we'll keep on increasing all the way to 0 for the points 1 and 4, and then we'll keep on increasing to pi again for the point 2. So for 3, we're going to fill out minus pi. Okay, so now we have the 4 different values between minus pi and plus pi. And then the next step to calculate the square root is just dividing by 2. So that's an extremely complicated calculation, which we're going to do right here. And then we see that we end up with arguments in the W plane from minus pi over 2 to pi over 2. So let's quickly sketch that. So this is the W plane compared to the Z plane over here. So an angle of minus pi over 2 is over here, and an angle of pi over 2 is over there. And we see that the angle increases from minus pi over 2 to pi over 2 over there. So indeed, we only have solutions for which the real part of W is positive. So these two situations, these two recipes to make our complex square root single valued are equivalent. Let's also check if we find the branch cut where it should be. So let's again just have our Z plane over here and our 4 points, 1, 2, 3, and 4. And let's see what happens if we, sorry, I have them wrong. So we have them numbered 1, 2, 3, and 4. So if we move from 1 to 4 across the positive real axis, then what will happen to our arguments? They will move from 0 to 0. So that's just a nice continuous change. So no branch cut over there. On the other hand, if we cross over from 2 to 3, then what will happen to our argument in the W plane is that we move from pi over 2 to minus pi over 2. So here we do pick up a pi phase shift, we do pick up a factor minus 1. So this is indeed indicative of the fact that over here we have our branch cut. So our branch cut lies along the negative real axis. And everywhere else, if you just travel from the point 3 continuously to 4 and then back to 2, you do not cross any branch cut, and the phase just evolves in a nice continuous fashion. So just to recap the phase of 2 pi, if you add 2 pi to any complex number z in the z-plane, number will stay where it is, no problem. If you have a complex number w in the w-plane, and to any of these values you add 2 pi, so for example you go from pi over 2 to pi over 2 plus 2 pi, then the location in the w-plane will also not change. The only thing that will happen is that if you add a factor of 2 pi in the z-plane, and then you use the recipe to halve that angle to calculate the result of the square root in the w-plane, then this 2 pi will become a factor of pi, and that will be the minus 1, that will be the phase change. The only place where adding 2 pi does make a difference is if you do it in the z-plane, you want to move to the w-plane by halving it.